This is Mr. T with a tutorial on a second part of implicit differentiation. You had a tutorial previously on introducing you to the concept of implicit differentiation, and today we're going to be working on a topic that allows us to solve what are called related rates problems. In this particular situation, we not only have, say, variables x and y that are related to each other in some way, but each of those variables are also changing with respect to time. To visualize that, we could view ourselves as, we have some object maybe, and that object over time is moving. And let's keep it simple. So let's say here this object is moving in a circle. So at any given time, the speed of the object would be represented by this vector on the tangent. So this is our velocity vector for that particle. And one of the things we learned in physics, if you've taken physics, is we can break a vector down into its components. We can break it down into how x is changing with respect to time, so our horizontal change and our vertical change. And there's a parallelogram method that you would know, but that's not really important here. So the speed of our object could be called dv dt, the rate of change of the velocity with respect to time, and that is broken down into a x component, dx dt, and a y component, which we can refer to as dy dt. Now, if this object is moving in a circle, if we put the origin here, and let's say this circle had a radius of 4, we also can relate x and y together using the equation of a circle. So x squared plus y squared equals, in this case, 4 squared, which would be 16. Now again, x and y relates the position on the coordinate plane at any given time, but also x is some function of time, and y is some other function of time. Now we know from the chain rule and from implicit differentiation, if these are functions of something, we have to apply the chain rule when we take the derivative. So in this case, we are going to be taking the derivative of this expression not with respect to x or with respect to y, but we are going to try to find how that expression is changing with respect to time. So we have our sum rule here, so we can take the derivative of each part separately. And now we can apply our derivative rule. So the derivative of x squared is going to be 2x. But then we have to multiply it by the derivative of whatever this function is with respect to time. So again, just like we envisioned when we did the implicit differentiation the first time, x is some expression here with the letters t in it. So inside, this x is a parentheses with a blob inside, so using our chain rule, we have to take the derivative of what was inside the parentheses. Since we don't know that particular function, we can't do that directly, so we represent that as dx dt. And likewise here we get 2y dy dt, and the derivative of a constant is 0. Now we have 4 different unknowns here: x, the rate of change of x, y, and the rate of change of y. Theoretically, we could solve, let's say we were trying to understand the rate of change in the y direction and how it relates over here. So I'm going to solve this equation for dy dt. So we have to subtract this to the other side. So it's going to be negative 2x dx dt. And then we can divide by 2y. And we are going to get over here that dy dt is, cancel out the 2's here, so we get negative x over y times dx dt. So this equation tells us how the speed of y, or the rate of change of y, how it relates with the rate of change of x. So these two rates are related to each other with this formula. So when we go into the examples next, and they're called related rates, we have two different variables that are related to each other, and they are also, their speeds or rate of change with time are related to each other. Hopefully this will become a little clearer when we go into our example, which is coming up next. Before we work a couple examples, let's talk about related rates problems. In these problems, as I discussed a second ago, we're going to have, in general, two variables that are related to each other, and they're both changing with respect to time. An example might be if you are blowing up a balloon and you're interested in how big the balloon is, say the diameter of the balloon is over time, and we might be assuming that we're blowing air in with a pump at a constant rate of change. Or you could envision dropping a rock in the middle of a pond, and if you've done that, you know that ripples start going out from the center of the circle, and we might be interested in how fast that area of that circle is changing, how fast it's getting a bigger area with respect to time. And I also have already mentioned that related rates problems are one of the main applications that we're going to use implicit differentiation for. Before we go into the specifics, you need to have a process. Many of you have issues or difficulties with word type problems, so all of our applications here are going to be word problems. So a good way to get started is to draw a picture of the particular problem, labeling the variables and writing down what it is that you're being asked to find, and writing that down in terms of algebraic or calculus expression. By drawing the picture, you will get a chance to understand how these variables are related to each other. Our next step is we need to write an equation that will relate the variables. So in our earlier example in the tutorial, we used an object moving around a circle, so we used the equation of a circle. If we were doing the balloon problem I mentioned a second ago, that would be, as you blow the balloon up, it's forming a sphere, so we would need to come up with the geometric definition of the volume of a sphere, etc. Sometimes our picture will be a right triangle, in which case then we could use the Pythagorean theorem. At this point, we can only plug numbers into the formula if the values or the variables that the numbers are for are something that's constant. So, for example, in the balloon problem, the diameter is changing over time, so we could not plug in a specific value for the diameter. You'll see this as we get into our examples. We're going to differentiate using implicit differentiation, both sides of the equation with respect to time. At this point, we can then substitute in the given values and solve for our desired item. So as we go into the examples in just one second, keep in mind this process. Okay, here's our first related rates example. We have a cone-shaped cup is being filled with water. We're told that the diameter of the cup is equal to its height, and that water is being poured into the cup at a constant rate of 3 cubic inches per second. And we need to find how fast the height of the water is inside the cup is rising when the water is 1 inch deep, and then also when it's 4 inches deep. So in our process, our first step was to sketch a diagram and label key variables in parts. So let's try to make a sketch here of a cone. So we have a circular top and our sides, and we are told that the diameter of this cup is equal to the height. So we have diameter equals height. We have water being poured into the cup, and it's filling the cup. So we have the water coming in here and filling our cup. Given that this is a cone, at any point in time, our height of the water is equal to that diameter, or if we show a radius here, since the diameter is 2 times the radius, so our radius is going to equal to 1/2 times the height. And we're being told that this water is flowing in at a constant rate of 3 cubic inches per minute. Cubic inches is volume, so we know that the volume of the cup, or the water, is increasing at 3 cubic inches per second. So we have our diagram. So our second step in the process is to try to write an equation relating the variables. So we are interested in height, and we are interested in rate of change of volume. So we need to write a volume equation. So we can look up, if you didn't know the equation, you could look it up on Google, but the volume of a cone is equal to 1/3 times the area of the base times the height. In this particular cone, the base is a circle, so we have 1/3 times pi r squared h. Now, to simplify this, we have 3 variables right now, and we would like to get that down to 2 variables, but over here we were told a relationship between diameter and the height, and we turned that into a relationship between the radius and the height. And we want to leave h in the equation because it's asking about height, so we want to substitute r with something, so we can substitute here. So I can rewrite this equation here, putting in 1/2 h, and that's squared, and times h. So if I simplify that, I'm going to get 1/4 here. 1/2 squared is 1/4 times 1/3 is 1/12. And then we have times pi. And we have h squared times h, so we have h cubed. At this point, we cannot substitute in numbers for volume or height. The height is changing, so it's not a constant. So we can't substitute any in. So our step 4 is to take the derivative of both sides of the equation with respect to time. So dv dt equals, now that whole thing is a constant, so we're going to have 3 times that, so we have 3/12, which is 1/4 pi, so I'm just going to put this pi over 4 times h squared, and h is a function of time, so we have to use our chain rule and tack on dh dt. Now we are trying to solve for dh dt here, so we're going to be substituting in numbers. So our first thing is, so first part here is when the water is 1 inch deep. So we want to know what happens, or what is dH dt when h equals 1. So if we plug into our equation, dv dt is 3. Now we have pi over 4 times 1 squared, and that's, I'm sorry, that's times dh dt. Now we want to solve for that, so we have to, that's just going to be 1. So we have to multiply by the reciprocal, so we have 3 times 4 over pi equals dh dt. So this computes to approximately 3.18. So dh dt is approximately 3.8, and our units here are going to be inches per second. So that's how fast the water is rising when we are down here at about 1 inch. Now we're going to let the water go a little further and see what happens when h is 4. So we can do the same thing here. So we're going to substitute in this time 4 for h. So this is 16 divided by 4, so we're going to end up with 4 pi here. So 3 divided by 4 pi is going to equal dh dt, and that is approximately 0.2 inches per second. So we can see as the water fills, it takes more water to raise the level. That would be common sense. So as the cup fills, it rises, the height rises at a slower and slower rate. So now we will be looking at our example number 2. So in this case we have a plane that's flying overhead at a constant altitude of 5,000 feet. It's flying horizontally at 1,000 feet per minute, and we want to find the rate of change of distance of the plane from the observer after 5 minutes. So we have our ground here, and we have an observer, and overhead we have a plane. Now I'm not a good artist, so I'm just going to represent that as a triangle. And we are told that the plane is 5,000 feet altitude, and it's staying at that altitude, and that it's flying horizontally. Let's call that distance x. And we are told that the speed is a constant speed, so we are told that dx dt is 1,000 feet per minute. And we want to find how fast this distance is changing. So let's call that, we'll just call that z. And this we can call y, but it's a constant. And we're trying to find dz dt when t is 5 minutes, and we're also trying to find dz dt when t is 12 minutes. Now we need a formula that will relate our letters here, and we have a, since this was a right angle here, we have a right triangle, which means the Pythagorean theorem applies. So we know that we have z squared equals x squared plus y squared, and since y is not changing with time, we can go ahead and plug that in. And so now we can take the derivative of both sides if we do step 4 of our process. So we're going to get 2z dz dt, because z is changing with respect to time, equals 2x dx dt. And then the derivative of this constant is 0. Now we're going to be working with dz dt, so let's go ahead and divide by 2z. So I'm dividing this by 2z. So the 2's cancel out, and I get x over z, and that's times dx dt. So now we can plug in. So at 5 minutes, we need to put this in terms of x and z. So at 5 minutes, I've traveled 5 minutes times my speed of 1,000 feet per minute, so I've traveled 5,000 feet. So that's my x. And I have to calculate z, so I have to calculate it using this Pythagorean theorem. So z is going to be the square root of 5,000 squared. So I'm putting the 5,000 in for the x, and plus the 5,000 squared. And if we take that square root and round it, we get 7,071 feet approximately. So now if we want to find our dz dt, we get x, which was 5,000, over z, which is 7, whoops, that's a 7. So again, let's go back here, dt. So we've got 5,000 for x over 771, and then times dx dt, which is 1,000. And if we multiply that out and round, we get approximately 707 feet per minute. So the plane's traveling at 1,000 feet per minute, but since we're down on the ground at this angle, our distance is changing at 707 feet per minute. Now we have to do the same thing at 12 minutes. So that's going to be, x is going to be 12 times 1,000, or 12,000 feet. And if we calculate our z, it's going to be 12,000 squared plus 5,000 squared, and that's going to give us 13,000. So our dz dt is going to be 12,000 for x over z, which we just said was 13,000. That's times 1,000 feet per minute, and that's going to give us approximately 923 feet per minute. We can sort of, if we use our intuition, as this plane gets further and further away from us, the angle here of z gets flatter and flatter. It gets closer and closer to being horizontal or parallel with x. So as the plane keeps getting further and further apart, the speed of or rate of change of z is going to get closer and closer to the rate of change of x. So if we took this out to an infinite amount of time, we would get 1,000 feet per minute as our apparent speed or change in distance. That really wasn't part of this problem, so our two answers are here. This is what it is at 5 minutes, and here is what we have at 12 minutes. So again, we've just been through two examples. We've got a process of drawing a picture, coming up with an equation to relate the variables, taking the derivative with respect to t using implicit differentiation, and then plugging in our given information to come up with our answer. So good luck on working these yourself.